When Luke Davies looks at a galaxy, he's literally looking back in time. The light hitting his telescope left its source before our solar system even existed. He's an associate professor at the University of Western Australia, based at the International Centre for Radio Astronomy Research in Perth. And for the last decade, he's been mapping how a galaxy's cosmic neighbourhood shapes what it becomes. He also helped break the news that the universe is slowly running out of energy, and somehow made that sound almost peaceful. I wanted to talk to him about deep time, the questions physics still can't answer, and what it does to a person to spend a career looking that far back. You spend your career looking at light that left galaxies billions of years ago. You were literally working in the past. When did that stop feeling strange, if it ever did?
Yeah, never, to be honest. It's a really weird thing to suddenly realize that you're looking at stuff that happened millions of years ago and is no longer going on. And I think it's one of the amazing things about astronomy that because of the finite speed of light and the time it takes light to reach us, we're always constantly looking into the past. So even the light from the sun takes about 8 minutes to reach us. So you're never actually seeing the sun as it is. You're seeing it as it was 8 minutes ago. And when you extrapolate that to some of the most distant galaxies, you're looking at galaxies that existed billions of years ago that are no longer there. And using that to try and understand the complete evolutionary history of the universe is a pretty amazing thing.
On that, with the, like you said, that some of these galaxies would no longer be, actually there. Do we know which ones? So obviously getting the light that, literally billions of years ago, but can we predict at the current moment which ones would be still, as they were, or how much difference there would be, or which ones would literally be non-existent?
So basically galaxies are changing all of the time. So you have situations where galaxies are taking gas, which is mostly hydrogen, and they're turning it into stars. And while they're going through that process of making stars, they're very, very bright and you can see them and they put out a lot of light. So some galaxies then actually run out of gas and they stop forming stars and we wouldn't see them anymore. And other galaxies merge with bigger galaxies all of the time. So the universe runs through this thing called hierarchical assembly, which sounds a bit complicated, but basically it means that you just start off with a load of small galaxies. And those galaxies smash into each other through gravity and form bigger galaxies. And those galaxies smash into each other and form bigger galaxies again. So when we look out into the very distant universe and we see galaxies that existed billions of years ago, what will have happened to most of those galaxies is that they will have actually combined to form bigger galaxies over time. So if you look at, say, our own Milky Way now, lots of the stars that are in the Milky Way now formed billions of years ago as well, and they've all combined together under gravity to make a big galaxy like the Milky Way today. So all of those galaxies that we're seeing in the distant universe billions of years ago, today in some other part of the universe that we no longer see, they're actually in much bigger galaxies that could be similar to the Milky Way.
And if I'm remembering correctly, so the Milky Way galaxy at some point in the future, we're going to collide with the Andromeda galaxy. Is that right?
Yeah. So Andromeda is our nearest large neighbor, and the Milky Way galaxy and the Andromeda galaxy are moving towards each other. And in a few billion years, the prediction is that they will crash into each other and form a much bigger galaxy, which some people have called Milkdromeda as the catchy name for it. Now, the question I always get when I say that to people is, what will it do to the Earth and the Sun when those two galaxies smash into each other? And the answer is absolutely nothing at all. The space between stars and solar systems within a given galaxy is actually massive in comparison to the actual size of those particular solar systems. So all that would happen was that our night sky would get brighter for a while, and there would be more stars in the night sky, and then the two galaxies would merge and you wouldn't really know much about it at all if you were still around on the Earth.
Yes, that's pretty mind-boggling with especially, I guess, like looking up into the sky and seeing a galaxy, but obviously it's essentially so spaced out that there's no risk of actually anything coming in contact with anything else.
Yeah, so the Andromeda galaxy is actually relatively large on the sky now, but you can't see it with your eyes really because the light's so spread out that it's actually quite faint over that large area. If you took the Andromeda Galaxy and you put it much further away from us, you'd actually be able to see it much more clearly because the light is more concentrated in a smaller patch of sky. So at the moment, it gets spread out over the sky, all of the stars, so it actually looks quite faint. So our ability to see things in the night sky is actually dependent on how concentrated the light is. And that's why we can see lots of stars and things, and we can't see lots of galaxies, because the galaxy light is actually diffusely spread over larger areas.
Right.
So the only real galaxies you can see with your own eye are the Large and Small Magellanic Clouds. And they're actually dwarf galaxies which are orbiting the Milky Way. So they're really nearby.
When you say really nearby, how far is that?
Oh, you've got me now. I don't know off the top of my head how far away they are. They're in cosmological terms, they're very, very close. Yeah. So they're actually gravitationally bound to the Milky Way. So they're orbiting around the Milky Way. And at some point, they will actually merge with the Milky Way as well.
Okay.
I was amazed the first time I saw the Small and Large Magellanic Clouds. So I grew up in the UK and did all my work in the UK. And I first came to Australia when I was about 20 years old to do some research. And I remember going outside and looking up at the night sky and actually seeing the Small and Large Magellanic Cloud for the first time. And it just completely blowing my mind because I'd never seen another galaxy. And it was just, absolutely mind blowing to see them.
Yeah, I don't think I've ever thought about that, actually. The feeling of looking up and seeing quite a different patch of sky. Yeah.
Yeah, it's one of the amazing things about being a researcher in astronomy is actually seeing some of these things for the first time. And astronomy is such an amazing subject because I think every single person when they were a kid has just looked up at the night sky and wondered about what's going on and been kind of amazed by it. And what I've found is the more and more I get into astronomy research, and I've been doing it for 20 years now, I still find those amazing things all of the time that I'm completely blows my mind that I'm the person that's getting to study this and look at it. And, sometimes you can get really bogged down in doing tiny little bits of science and banging your head against a brick wall of trying to get something to work out, which is quite abstract away from what you're doing. And then suddenly you just have this moment where you see something and the sort of enormity of it dwells on you and it completely stops you in your tracks. I had a moment during my PhD where I was working for months on trying to get these observations of very, very distant galaxies in the early universe to work. And I was struggling and it was taking me months. And I was just looking at computer code and I was banging my head against this wall and I couldn't get it to work out. And I finally got it to work. And I got this picture come up on my screen of this little tiny blip of light that was light from a galaxy that existed about 12 billion years ago. And I looked at that and I just thought, that light has traveled through space for 12 billion years to reach the Earth, and it's hit a camera at the Earth, and I'm managing to see it. And then it dawned on me that I was the only human that had ever seen the light from that galaxy. No other human had ever seen it, and it just completely blew my mind. And it was one of the points where I really decided, astronomy is a career for me, and I'm gonna carry on doing this for the rest of my life.
Wow, yeah, cool. That's actually giving me goosebumps. So that's really cool. Taking yourself back to when you were younger, what exactly or specifically was it about galaxies that drew you in and not, looking at stars or planets or, more, I guess, zoomed in sort of things?
Yeah. So if I'm honest, when I was young, I didn't really think about being an astronomer that much. I liked looking up at the night sky and I wasn't like, yes, this is for me and this is what I want to do. And I went through school and then through university, and I really liked physics. I liked understanding how the world worked. If I saw a ball drop or something fall off a table, I was always kind of like, oh, well, why does that happen? And I did physics in school. And then when I went to do my undergraduate degree, there was a course in physics with astronomy. And I thought, oh, that sounds kind of cool. I kind of like astronomy stuff as well, so I'll do that. And it wasn't really towards the end of my degree, probably in the fourth year, where I suddenly realized that I really started to like astronomy and this was the bit that was for me. And then I sort of ummed and ahed about doing a PhD and got sort of pushed into it a little bit by a supervisor who thought I'd be quite good. And then during my PhD, I just completely fell in love with it. And I think for me, I like to understand the answers to big questions, I suppose. And astronomy felt like the biggest questions that you could ask, like why does the Earth exist? Why does the galaxy exist? Why are we here? Why is the universe working in the way that it is? And I got really into some of that big picture stuff. And I think in astronomy, the biggest things that you can ask are really about cosmology. So like the structure of the universe and how the universe evolves. And if I'm brutally honest, I don't think I was good enough at maths to do cosmology. My maths is probably better than the average person, but I wouldn't say it's particularly great. And I think to understand cosmology and to make really good advancements in that, you need to be very, very good at maths. And the next thing down on the big picture scale was understanding galaxy evolution. And it just sort of really scratched an itch for me, I suppose. It wasn't quite that abstract as cosmology, when it's a lot in the world of maths and numbers and long equations. You could physically see and understand the things that you were doing, but it was still this big picture of, why does the universe we see today look the way that it does? Why do galaxies exist in certain parts of the universe? Why do stars form, and how does that impact galaxies, and what happens when galaxies smash into each other and things like that? And it just felt like it was the perfect match for my personality as to what I was interested in. And ever since, I've just completely loved it.
Yeah, I can imagine that. I'm similar. Obviously, nowhere near as good at maths as you would be either. But the idea of actually seeing the things with your eyes sounds very intriguing, rather than just on paper doing equations.
Yeah, I did a public outreach event at a primary school at the end of last year, and I arranged for a load of telescopes to be there for the kids to look at the night sky. And we were in the middle of Perth, and it was a bright night, and we decided the only things we could really look at were the moon, and then Saturn was up, and you could see Saturn. And through these telescopes, you could just a tiny little bit make out the rings of Saturn. So Saturn looked like a black blob, but it had a little horizontal line through the middle. And I was sort of thinking, oh, these kids are going to be bored. They see the moon all the time, and you can barely see Saturn. And I was sort of the impression, oh, this is going to be a bit of a washout. No one's going to be happy. And the amount that those kids were amazed and super excited and enthused and running around shouting at each other that they could see the rings of Saturn was kind of crazy. And it's just that ability to, yeah, you've seen these beautiful pictures of Saturn from the Hubble Space Telescope online, but there's something about physically looking through a telescope and seeing that for yourself that just brings it massively home, that these aren't just abstract pictures you see on a computer. They're real physical things that are out there. And it was just amazing to see all these kids just super excited to see this little blob on a telescope that really didn't show you that much.
Yeah, that's definitely the sort of, well, it's still with images, but I guess the recent sort of NASA a mission around the moon with some of those photos sort of elicited some of those similar feelings in myself, that you sort of got a different perspective, even though it was still photos. I found that pretty incredible.
Yeah, I completely agree. Just seeing those people out there and them sort of talking in real time with close-up pictures of the moon next to them, it's just something, it's completely different to actually seeing pictures of it taken from a long distance away. It really brings that whole scale of the cosmos, I suppose, like down to you. The fact that it took them days to get to the moon, and the moon is pretty nearby, to be honest, in comparison to everything else, just really hammers home sort of the enormity of the cosmos.
I think I wanted to ask you, or main part is about some of the work you've been, well, I think it was about over a decade, so the work you did as part of the Devils project. Would you mind just firstly explaining what that project was?
Yeah, so basically when we try and understand galaxy evolution and how galaxies work, we try and get as large a sample of galaxies as possible. And what we try and do is we try and measure all of the properties of those galaxies. So we bring in data from loads and loads of different telescopes, and we try and understand things like how many stars a galaxy has in it, how much gas it has, how many stars it's forming, and lots of those different properties. Now, one of the biggest problems we have in studying galaxies and how they evolve is actually measuring how far away those galaxies are from us. So what we'd ideally like to do is to build like a three-dimensional map of the universe where all the galaxies are, and then try and understand all of the galaxies within that three-dimensional map. As I mentioned before when we were talking about the beginning, because of the finite speed of light, the further you look out into space, the further you're looking backwards in time. So what you can do is you can look at galaxies which are really far away from you, and then you can look at galaxies which are a little bit closer, and then a little bit closer, and a little bit closer again, all the way down to being nearby to the Milky Way. And what that gives you is actually a timeline. So you can say, how have galaxies changed across that timeline? Now, measuring those distances so you actually know where to put your galaxy on a particular timeline is really difficult, even with the most massive galaxies and massive telescopes, in the world. The reason is that to measure the distance to a galaxy, you need to measure this thing called a redshift, which people might have heard of before. The only way to measure a redshift is to get a spectrum of the galaxy. And what a spectrum is like it's like getting a rainbow of the light that comes from a galaxy. So the way we do that is you put an optical fiber down on the galaxy, and you get light come through that optical fiber from a telescope, and you spread that light out onto a CCD camera, and you measure how much light you get as a function of wavelength. And using that, you can work out the redshift. And if you understand how the universe works, you can turn that redshift into a distance. Now, measuring that spectrum for a galaxy means that you have to point the telescope, or some of the biggest telescopes in the world, at a galaxy for a really long time to sort of make it as simple as possible. So what we do is we try and get as many galaxies as we can in a large survey, so that we get more statistics, I suppose, in each evolutionary time step to work out how galaxies change with time. So what we did with the DEVIL survey was we picked 3 regions on the sky that were relatively small chunks. So if you looked up at the night sky, they'd be a little tiny patch on the night sky, basically. And what we tried to do was we tried to measure the distance to every single galaxy down to some very, very faint brightness in that patch of sky. So what people have done before is they've actually tried to do sort of larger areas of the sky and get brighter galaxies. We went for tiny little areas of the sky and get really, really faint galaxies. What that means is that we're actually looking out further into space than the other surveys have done before. And that means we get a longer evolutionary baseline because we're looking further out in time. So what we did was we took these patches of sky, we then looked at them for nights and nights and nights using the Anglo-Australian telescope, which is in Siding Spring in New South Wales, which is the biggest optical telescope in Australia. And after doing this for a number of years, basically, looking at these patches of sky, we actually have the distances to tens of thousands of galaxies in these little patches of sky. We then use those spectra to measure the redshifts, and using that, we build a 3-dimensional map of the entire universe in those patches of sky. So we then have the structure of the universe, we have where all of the galaxies live in that structure, and then we also have an evolutionary timeline from about 8 billion years ago to today. So we then start doing science with that sample. So we measure all of the properties of the galaxies, things like their stellar mass, like I said, and their star formation and things like that. And the key piece of science that we're doing is we're cross-correlating the properties of the galaxies with where those galaxies live in the universe. So the work that I've been working on with the survey for the last few years is really to say, how does where a galaxy live in the universe change its life cycle? So what we know about in the nearby universe when we look at galaxies is that there is a strong correlation between the properties of a galaxy and where it lives. So if a galaxy lives very nearby to lots of other galaxies, it actually has measurable different properties than if it lives on its own in a very isolated part of space. So I like to sort of liken this to the fact that if you grew up in a big city and you were surrounded by loads of other people all of the time, your life might be very different to if you lived in a really isolated remote island away from everybody else. And the same is true for galaxies. So galaxies that live nearby in these really dense regions, they act very differently and have very different lives to galaxies that live in these very isolated regions. In the local universe, we can see that happens and we can measure it, but we don't really know why. We have some ideas about why that happens, but essentially we need to go and look at galaxies over this evolutionary baseline to try and work out why those correlations happen. So the point of DEVIL was to trace where these galaxies live and their properties over a really long time period to work out why those relations came to be. And that's what we've been doing. And what we've found is that galaxies that live in these overdense regions with lots of other galaxies around them, they actually form less stars. They're more massive. They look quite different to the galaxies that grow in isolated regions. And for the first time, we're building this sort of complete picture for how where a galaxy lives impacts its life cycle and how it works. So we can now build these models for how galaxies change over time depending on where they live in the universe.
Sounds like a lot of data you've come up with.
Yeah, there's been lots of students and postdocs working on this for quite a long time. And it's kind of interesting that it's this intermediary project between two other projects that we're doing. So we started off doing a project called Gamma, which tried to do similar things in the local universe. And then we did Devils, which extended out this analysis into the more distant universe, so over a longer evolutionary time. And then we're just about to start a project called Waves, which is doing a similar thing, but over much, much larger areas to cover a much broader parameter space of galaxies in the universe. And we've been working on Gamma, we worked on for about 10 years, and then Devils was about 10 years. And then we've been planning Waves for the past sort of 12, 13 years. And as of July this year, hopefully it's going to start. So I've just come back from Germany where we've been having a big meeting about making sure we're all ready to start all the observations for Waves.
Yeah, awesome. Great. So you mentioned and I've seen you make the analogy of sort of where you grow up has an influence on, basically personality and different things. And obviously same thing with the galaxies, but what were the biggest sort of things that jumped out as being, quite interesting or I guess surprising about the region and what you saw?
Yeah, so the biggest thing I'm interested in with this really is how galaxies form stars. So when you have a galaxy and you have lots of gas around in that galaxy, that gas is mostly hydrogen and helium, and it condenses down as it gets cool. And when it gets cooler and cooler, it gets pushed down under gravity. And then at some point, nuclear fusion starts and stars are born in these gas clouds. That's happening all the time in galaxies, and that's how our sun was formed, basically. So the interplay between this gas in galaxies and its ability to form stars is one of the important processes that occurs in galaxies that allows galaxies to grow bigger by making new stars. Now, what we find in all of the work that we do, particularly with Devils, is that where a galaxy lives in the universe can actually impact the rate that this gas condenses down into forming stars. So if you imagine that's the primary way that a galaxy gets bigger over time, if you stop that from happening, the galaxy stops growing. So it's kind of a bit like, you can think of it as the gas being the food that helps the galaxy to grow. So imagine that you have lots of gas around and it can easily make new stars. That's like giving someone loads and loads of food and they're going to get bigger and bigger and bigger. And then if you suddenly stop that food, you starve the galaxy and it can no longer form any stars. So obviously, if that happens, it changes the way that a galaxy looks and how that galaxy changes with time. So in these surveys, what we find is that if you are a galaxy that's sort of falling into a region with lots of other galaxies around them, you actually stop that galaxy from getting the gas that it needs to form new stars. So you're basically starving it and cutting off its food supply. And that means that that galaxy will no longer grow any bigger. And you can actually see this in the observations that galaxies that are falling into these big overdense regions of other galaxies, they stop growing because they're not forming any more stars. You can also see things like when two galaxies are going to smash into each other, just like the Milky Way and Andromeda will at some point, you actually give the galaxies sometimes more gas and you churn up the gas, pushing it together. So you actually form more stars when you push these things together. So what I'm really looking at is how these different environments where they live, how they form more stars. So to go back to the analogy of like these two galaxies smashing together, it's because you live in an overdense environment, like you live in a busy city center, you have more access to things like McDonald's or Burger King or things like that. So you can form more stars. If you live in a really isolated region of space and nothing's happening to you, you don't have access to those things and potentially you don't grow quite as fast.
Okay. So with the WAVES project is, how much bigger is that going to be?
Yeah, so WAVES, in comparison to DEVILS, we actually have two parts of the WAVES survey. One of them is doing a survey of galaxies in the nearby universe, and that's going really, really wide. It's not directly comparable to DEVILS, but it's going to cover sort of, it's going to go basically much fainter, so to go to fainter galaxies, which are basically smaller galaxies in the local universe. And it's going to be a massively huge improvement over what's been done before. The part that I'm really interested in is something called WAVES Deep, which is comparable to DEVILS. So what that will do is a similar survey to DEVILS in terms of the galaxies that it will see, but it will do about 15 times the volume of the universe. So what that means is that all of the error bars on all of our data get 15 times smaller, so you can say a lot more about everything that's going on. It also means that you're probing more different types of regions in the universe. Imagine if, say, with DEVILS, I'm looking at these environments and I might have got one city, one small town, and one isolated region that I'm comparing to. I'll now start to be able to map out, say, all of the cities on a continent and all of the towns on a continent. And that just means I get a better understanding of what's going on, essentially. The problem we have with WAVES right now is that it's going to take us about 5 years of constant observations every single night, pretty much, for the next 5 years to get the sample that we need to do that. So we start observing with this new telescope that's pretty much been built just to do these types of science in Chile, in South America. It will start observing in mid-July, and then we'll go for 5 years until we get the sample that we need to do all of our science. So it'll have been 12, 13 years of planning WAVES, and then 5 years of taking observations before we actually get to do any of the science that we want to do.
Okay, so a bit of a waiting game then.
Yes, yeah. Long-term projects.
Yeah. I saw you also noted that you've released the data from the DEVILS project out to sort of, whoever wants to try to, do some interesting work with it. Has that been out for a while? Has anyone actually, been doing anything cool with it, or is it still too early days?
So it went public at the end of last year. I've had lots of people contact me about using the data and asking questions and stuff about it. So scientists around the world. I've not seen any of publications officially come out yet from that, but I know there's quite a few in the pipeline. So what we try and do with all of our data and all of the science that we do is to try and process it in such a way that it's easily usable by other people, and combine it in ways with lots of other data so that people can easily find the things that they need to find. And then we upload them to sort of public archives and databases that we have a group here in Australia called Data Central, which is run out of Macquarie University. And they're world experts in how you provide astronomy data to the public so that they can use it in an easy way. So we work with them to put all of that data out there. So our sort of ethos is the more people who get to use this data and look at it, the more science will get done. So part of our job is to try and make it so that people all around the world can easily use it and do their own science. And hopefully what that means is that we just keep forwarding our understanding of the universe in as interesting a way as we possibly can.
Shifting a little bit, what does it even mean that the universe is slowly dying?
So this first came up as a press release we did for the Gamma survey a few years ago that I was talking about, the one we did before DEVILS. Despite it sounding very good for a headline, what it actually means is that when I talked earlier about gas collapsing down and forming stars, essentially, you can measure the rate that is happening in the universe globally. So we can actually measure how quickly gas is being turned into stars across the entire history of the universe. And what we find is that for the first sort of 2 billion years of the universe, the amount of stars that were being formed from gas was going up and up and up. And then it hit a peak about sort of 11 billion years ago. And now it's actually been slowly declining. And we can actually measure that decline, so how fast the universe is slowing down in the amount of stars that it's forming. So what that means is that the rate that galaxies are growing through forming new stars is getting slower and slower all of the time. What you can do is you can actually extrapolate that forward in time, and you can work out at which point the universe will stop forming stars completely. And that's going to happen based on those predictions in like 100 billion years time or something. So not something we have to really worry about too much now. So many times the age of the universe already. But it's an interesting number that you can basically pull out that says that within that period of time, the universe will just stop forming new stars. And that's one metric for how the universe is essentially dying. Because there are lots of different ways that you could define when the universe dies, but one way is to say that the universe just stops forming stars completely, and we can actually make a prediction for when that should happen.
Yeah, because I've heard obviously when people talk about the expansion of the universe and the sort of the heat death and everything, but the actual stopping the formation of stars is sort of a separate thing as well.
Yeah. So the way I like to think of it a bit is that like the universe went through its early period where it was growing and getting bigger, and then it sort of peaked in its teens and it reached the maximum rate that it was growing, and now it's sort of just slowing down, and we're just sort of tailing off into middle age, and then eventually it'll just get older and older and slower until it eventually pops its clogs.
Do you more on a personal level, like when you sort of hear those terms, and obviously that length of time doesn't mean much for a human lifetime, but the actual sensation that there won't be really anything left in the future, even though it's so many trillion years in the future or however long, how does that sort of resonate with you?
I think it's really strange to get your head round, to be honest, anything to do with astronomy. Like even things like how far away the moon is kind of mind-boggling when you actually think about it. So it's really strange when you're studying things on timescales of billion years to actually kind of comprehend as a human being what it is. And I think the main thing that it does for me is that it makes me feel massively insignificant. When you think about the size of the universe and the timescale of the universe in comparison to you as a person, it's so completely different, those scales, that it's really hard to not think that you are so tiny and insignificant. And it kind of pushes me to think that, I don't know, on a philosophical level, that the point of my life is really just to have a nice time, be kind to people, and to actually just enjoy the things that I'm doing, because it's so fleeting and tiny in comparison to this whole history of the universe and the whole future of the universe, that's all you can really do.
Yeah, it doesn't ever. Do you ever feel yourself slipping into the other side where it's a bit more nihilistic?
A little bit, but I think I always go the other way. I always think that my life is completely pointless and there's no meaning and there's nothing really that I can do. But then I flip over and say, well, that means even more so that I should just do the things that interest me, have a nice life, enjoy time with my friends and family and things like that, because it kind of is insignificant. And I don't think there has to be a meaning or a purpose for you to actually find enjoyment and happiness in life on your own, and just to do the things that you want to do. I think I'm super fortunate that I get to do a job that I love, and I like coming into work every day, and I find it exciting and infusing and intellectually stimulating to be here and do the things that I do. And I'm just kind of grateful that I get to do that. And I'm going to enjoy my short life for as much as I can before I disappear. And then I'm just a tiny little flicker of an eyelid in the whole history of the universe.
Yeah, I think that's right. I probably can sense that way. If you spend so much time thinking about the vastness and the pointlessness of it all, that when you sort of bring yourself back down to more of a human level, it might actually give you a bit more sense of connection and purpose overall.
Yeah, I suppose I'm not one of these people who feels there needs to be a point, I suppose. I from studying astronomy, it makes me realize that it's very highly likely that there's no point at all. But then the point is probably just for you to enjoy yourself and to have a nice time, as long as you're not hurting anyone else.
Yeah, I think it was a few years ago, at least 5 years ago, if not more. But there was some work that I saw your name come up in relation to. It had lots of numbers and letters, a long sort of title that wasn't very easy to read. But it was about the detection of two neutron stars colliding quite a while ago. I think there was like a video that maybe co-produced or something that I was looking into. But would you mind explaining, or first, what a neutron star is, and if that sort of if you remember the details of how that detection took place?
Yeah, so neutron stars are basically the densest object in the universe that we understand. Black holes are essentially denser, but we don't really understand what's going on in a black hole. So what neutron stars are when you have a very, very massive star, that star can run out of its fuel that it needs to keep itself stable. So what a star is basically a massive fusion reactor. You've got hydrogen or other elements in the middle of the star, and they're being crushed together to produce energy. And that energy basically gets radiated outwards. And that's what you see from the sun, basically. It's this basically hot ball of plasma that's going through nuclear fusion. Now, when massive stars actually run out of hydrogen and they can't form any more energy, what happens is that there's no longer energy pushing outwards from the fusion reactions, and there's a lot of gravity trying to pull that star in. So what happens is that the star collapses down on itself very, very quickly under gravity, because there's no longer any energy holding it out. And you get something called a supernovae or a kilonovae, which is a massive explosion that blows the star apart. But then you get a central part of the star that's really compressed and crushed down under gravity. Now, what a neutron star is when you crush that central region of the star down so much that all of the electrons get crushed down into we call it the lowest energy state, but it's basically them just getting crushed down really close to all of their protons. And a neutron star gets crushed so much that the protons and electrons actually fuse to become neutrons. So what happens is that you have neutrons and protons in the center of an atom, and you have electrons around them. The electrons and the protons get crushed down so much that they form neutrons as well. So you end up with this central part of a star, which is just made up of neutrons and is really, really dense. So if you had sort of the material of a neutron star, the density of it is basically like compressing the whole of Mount Everest down into something the size of a cardboard box. So imagine if you could crush Mount Everest into a cardboard box, how dense and heavy that would be. That's how heavy neutron star material is. So these neutron stars are really super dense. They spin really, really fast, some of them, and they produce these things called pulsars. So if you've heard of a pulsar, that's a neutron star that's rotating around really, really fast. And they beam out light from their poles, and it's kind of like a lighthouse spinning round, and that's what a pulsar is. One of the super interesting things about neutron stars is that you sometimes get two of them near to each other. And they can actually get so close that they get gravitationally bound, and they spin around each other. And then ultimately they merge together and form a bigger neutron star or a black hole. When they're spinning around each other, they release gravitational waves. So basically what happens is that if you change the distribution of mass in the universe, the gravitational field in the universe changes. So imagine if I suddenly change the gravitational field, it changes everything in the universe, and this sends out ripples through the universe, which is it kind of readjusting to the gravitational field. And that causes these things called gravitational waves. So they were predicted by Einstein about 100 years ago to exist as part of general relativity. It wasn't until about sort of 10, 15 years ago that we detected them for the first time. The way we detect these gravitational waves is through these neutron stars merging, because they produce big enough gravitational waves that you can detect them at the Earth. So at the Earth, we build these they are telescopes where they have two lasers in an L shape. And when a gravitational wave passes through the Earth, it actually causes the Earth itself to crush in one direction and stretch in another direction. So imagine them being like waves in gravity, essentially, that cause all of the Earth to compress and stretch. With these massive lasers, you can actually detect that stretching and that compressing and measure these gravitational waves. Now, by the amount that that stretching and compression occurs, you can actually work out which two things in the distant universe merged. So over in the distant universe, two neutron stars merge together. The gravitational waves go all the way through the universe. They stretch and compress the Earth, and we can measure that. and we can actually work out the mass of the two neutron stars that merged in the distant universe. Now, you talk about like mind-blowing things. I don't work in this field. That completely blows my mind. I think it's unbelievable that we're kind of measuring at the Earth the whole universe redistributing its gravitational mass distribution through neutron stars merging. Now, the other super cool thing about neutron stars is that the way that all of the elements of the periodic table are made in the universe is through stars. So stars basically take hydrogen and helium, the two smallest elements of the periodic table, and they make everything else. So everything you see around you, from the air you're breathing to the desk to trees, all the atoms that are in those that aren't hydrogen or helium pretty much were made in stars. Now, even the most massive stars aren't big enough to make some of the elements of the periodic table because they don't have enough energy within them. Neutron stars merging together is actually one of the places in the universe that has enough energy to make some of the missing atoms of the periodic table. But some of those atoms are actually quite common to us here on Earth. So anything that's made of gold or silver or some of the precious metals that you have in your phone that allows your phone to work, they were actually made when these two neutron stars smashed together. So they're the only sites in the universe, we think, that have enough energy to make things like gold. So if you're currently wearing any gold jewelry, that jewelry was actually made when two neutron stars in the distant universe smashed into each other. So you literally have on you right now probably part of something that was made when neutron stars smashed together.
That's incredible. Yeah, that's amazing. That's one of the most mind-bending things, I think, knowing that it can be literally right with you rather than, seeing it out at a huge distance, but amazing.
Yeah, I think it relates completely back to what we were saying at the beginning about bringing astronomy into the physical that you see around you, shows you the excitement about it. Like the fact that you can say, yeah, my ring was made in a neutron star merger kind of just hits it home. I've actually got my wedding ring is a meteorite actually as well, which cool. I always love to sort of bring me close to space to know that this was flying around the solar system at some point before it made it to my finger.
Gee, so what's that actually made of then? Like elementally?
So it's a meteorite band, and then it's got titanium in the middle. Yeah. So it was etched out of a meteorite with acid. And me and my wife have got matching ones.
That's cool.
From the same meteorite.
That's really cool. Wow. That leads me into maybe a bit more of uncertainty realm. What do you think that over the next, I know it's a bit hard to predict what we're going to be, discovering and thinking about differently, but at the moment, what do you think is maybe something that we're not thinking about in the correct way, or that might be missing a few key details?
Oh, that's difficult. The one thing that we're really missing key details on is this thing called the Hubble constant. So I think one of the biggest things we don't know right now is what the Hubble constant actually is as a number. So what the Hubble constant does is it basically describes how fast the universe is expanding. So we can measure from looking at galaxies and the distribution of galaxies in the universe and how they're moving, how fast the universe is expanding. Now, this measurement actually tells us sort of how old the universe is as well, and when the Big Bang was, because you measure how fast the universe is expanding, and then you just basically turn the clock back and say, when was everything in one single point? Oh, that's the Big Bang. But we don't quite know how fast the universe is expanding. The reason for this is that there's two separate ways for measuring the Hubble constant. One of them is to look at how galaxies are moving away from you, basically. So we would call this a radial velocity, so how far away something is moving away from you. The other one is to look on scales to see how far galaxies are moving apart from each other tangentially across the sky. Now, those are completely different methods of measuring the Hubble constant. One of them uses redshifts, and the other one uses this thing, basically uses the cosmic microwave background radiation, if you've heard of that, and looks at how that's distributed and galaxies are distributed. The interesting thing is that those two different methods actually give different answers right now. And you go back about 20 years, And those two answers were slightly different, but within the error bars overlapped. And we sort of said, okay, well, we just can't measure these things well enough, and they're probably the same, but we just don't have good enough measurements to say that they're the same. As time has progressed, the error bars have gotten smaller and smaller, but the numbers haven't got closer together. So what's happened is those two methods for measuring the Hubble constant have actually now separate from each other, even with the errors included. So we have one that says that the universe is expanding with the number about 71 or 72, and this is in weird units of kilometers per second per megaparsec or something like that, which are weird units. The other one says the number should be closer to sort of 67, 68. Now, those seem like small differences, but we've now measured those things to such a degree of accuracy that they aren't consistent with each other within quite a few sigma, which is basically the error on the distribution. So there is a tension currently in what the Hubble parameter is. Now, this will probably be resolved with the fact that one of those methods is actually quite harder to measure than the other one, and there's probably some systematic thing in it that we've got wrong. But as it currently stands today, we don't know why those two things give different answers. And at some point in the near future, I think they'll have to converge, but we don't quite know why they're different at the moment.
Okay. Yeah. And I've also seen that there's some of is it from the James Webb telescope, where like some of the galaxies they were seeing that appear to be sort of too old for, they shouldn't have formed the way they had. Have we sort of resolved that issue, or is that still a big question?
No, that's still an open thing as well. So what this is that there are galaxies and supermassive black holes in the early universe that James Webb has been detecting, that if you put in a model for how we think galaxies should turn gas into stars, like we were talking about before, the universe isn't old enough for them to have grown so big. So if you say, oh, well, we think we understand how gas turns into stars, we say that based off that model, these galaxies needed 4 billion years to grow as big as they are, but we observe them when the universe is only 2 billion years old. So they currently haven't had enough time to grow. There are two solutions to this. One is the universe is older than we think, and they have had long enough to grow, which is quite unlikely given other measurements that we have. The other option is that we don't quite understand how stars form from gas, and there is a different mechanism, and there's things that we don't understand about that. There is a lot of work going on to try and resolve this inconsistency at the moment, particularly where I work at ICRAR. There's a huge amount of work going on. We work observationally with James Webb to do science, but we also have a simulations group which are trying to simulate the universe and how galaxies form to try and work this out. And they think currently there are some simulations which can actually get the right answer and reconcile this without making the universe 2 billion years older, but it's still a bit TBD as to what that solution will be. My personal feeling is that it'll just be that we have to tweak things slightly in how we think stars form to be able to get those galaxies, or that galaxies are merging more quickly and things like that as well. But to me, I don't think that'll be a thing which kind of breaks big things about our understanding of the universe.
Yeah, I've heard a few people postulate about that the universe might be older, but it seems like there's quite a lot of other data that would have to be thrown out that doesn't seem likely to come to that conclusion.
Yeah, you'd have to change quite a few things. It's not doable, but you'd have to come up with a solution that worked for lots of other observations that we have. Because in things like the age of the universe and how the expansion of the universe works and things like that, we have quite a lot of independent pieces of observational evidence that suggests that they all kind of converge on the same answer, which means you'd have to come up with a model that not only fixed those galaxies being too massive, but also didn't break everything else.
Yeah, okay. Do you do any part of your work contemplating or trying to research dark matter?
Yeah, so we actually do a lot of this with waves. One of the main science cases that we're doing with waves is to try and actually understand what dark matter is. So for your listeners, just as a primer for dark matter, so the dark matter is really just the fact that when we look out into the universe, you can actually measure how big things are using the amount of light that they emit. So if you look and measure the amount of light that you see from a galaxy or from a cluster of galaxies, and you say, okay, well, I understand that that light is coming from stars, so I can work out how many stars are in that galaxy, and I can add up all of that light. You can then also measure the mass of something using gravity. So you can use even Newton's equations for how gravity works, but more formally Einstein's equations of general relativity to say, if I can measure how something's moving in a gravitational orbit, I can work out how much mass there is. Now, if you compare the mass that you get from the light with the mass that you get from gravity equations, they don't add up at all. They're completely different. Gravity would tell you that there's way more mass there than you get in the light. And this is why we think there's dark matter. Dark matter basically is just saying there is matter there, which we don't see in the light. So it must be dark. So we see it through gravity, but we don't see it through light. Now, that sounds a bit sort of hand wavy, where people go, well, maybe gravity is just wrong. And some people try and explore that as well. We have theories which say that Newton's view of gravity is completely wrong, and that's called modified Newtonian dynamics. And people try and use that to explain why you don't need dark matter. But the problem is there are lots of different observational pieces of evidence that suggest that dark matter exists in the universe, and they're all quite independent observations. So we think we're pretty certain that there is this stuff out there, which we call dark matter. But what it actually is, we don't know. We only know that it's stuff that we can't see that interacts not very well with everything else, and only really interacts through gravity, as far as we can tell. So basically, the hunt is on for finding what dark matter is. There are lots of different ways you can try and detect what it is. So there are people who build experiments in deep mines on the Earth who try and detect dark matter particles passing through the Earth, that they can find them in these big scintillation chambers and things. But you can also try and test it astrophysically as well. So one of the ways you can do that is you think that if dark matter actually interacts with itself, it might produce a signal that you can measure, and people are trying to look for that signal in space. One of the other ways to do it is that different models for what dark matter is actually result in different structures in the universe. I'll try and briefly describe that. So if you think that dark matter is something that interacts in no way with itself or with any other particles except for through gravity, if you build a simulated universe that has dark matter like that in, and you let it evolve to the present day, it has a distribution of galaxies that looks a particular way. If you then said, oh, well, dark matter is slightly different, and it actually interacts with itself a tiny little bit, and it interacts with other matter a tiny little bit, but we can't quite measure that right now. You build a simulation like that, and you let it evolve to the present day. The distribution of galaxies actually looks really different. So the question is can we make different models of dark matter in simulations and produce different universes today? And then if we actually measure the galaxies in the universe, can we differentiate between those different models? So the easiest way we can do this is by looking at these overdense regions of galaxies that I talked about earlier within devils and waves, where we're looking at the galaxy's environment and where they live. The number of galaxies that live in each of those environments is actually related to the model of dark matter that you use. So if you have a model of dark matter where it doesn't interact at all, you'll actually see tons and tons of galaxies in these overdense regions. If you just sort of crank up how dark matter interacts with itself, you'll get less and less galaxies. So what we're trying to do with waves, we can't do this with devils, and we haven't been able to do it with any other survey we've done before, is actually measure the number of galaxies in each of these different environments and try and see if we can differentiate between different models of dark matter. We're not sure whether we can do that yet. We don't even know if the waves data will be good enough to do it right now, but we're going to try and test it. And hopefully we can put some constraint on what dark matter is from looking at the distribution of galaxies in different environments. So come back in 10 years' time, and I might be able to tell you that we've actually put some constraint on dark matter from doing the wave survey. My personal feeling is that I reckon that one of the experiments which is building big scintillation vats of material down in deep mines on the Earth, at some point in the nearish future, we'll actually detect a dark matter particle passing through it. That's what my money's on. I think the particle physicists will detect it before the astronomers. And I think they actually get a clearer signal of what dark matter is. So I reckon if you come back in 20, 30 years, we might actually know a lot more about what dark matter is. We know it's out there, and we know that it's having a big impact on the way the universe looks. It's just that if it is something that only interacts through gravity, it's going to be really, really hard for us to detect, but we might actually do it in the near future.
Cool. Yeah, that's very exciting. Hopefully sooner rather than later.
That's a follow-up podcast for you in 20 years' time.
Yeah, definitely. Let's see, a few more grey hairs. One of the last things I wanted to chat to you about was more from a science communication standpoint. Obviously, you're quite big in this space, done lots of different events, and you've shared a stage with a couple of sort of like quite big names across global in science communication, like Neil deGrasse Tyson. You were sort of as part of an event that he was on, and Brian Greene. Is that right?
Yeah.
Yeah, cool. What did you learn from sort of spending time just in their proximity and seeing how they went about holding a room and the way they presented themselves specifically?
Yeah, so first one I did was with Brian Greene, and it was actually amazing for me. I was pretty awestruck. So I, as a teenager, read The Elegant Universe, his book, and really loved it. And I got to meet him backstage before we did the event, and I actually sat down with him for about an hour, and he talked to me about string theory and explained things that I didn't understand about string theory. And he was an incredible communicator, taking a really complex subject, explaining it in a great way with passion and enthusiasm, which I was just in awe of. And I think it really helped me understand how you take some of these really complex topics and dumb them down is the wrong word, but describe them in a way that someone who knows little about it can understand. Because I wouldn't pretend to understand much about string theory, but by the end of that conversation, I felt I knew all of it. And he was a really nice guy who was really great. And I think he infuses a passion for that kind of complex subject that is hard to understand. And you can see he really gets some enjoyment out of being able to describe that to people. And I think I have to say now, and likewise working with Neil deGrasse Tyson, he is someone I feel who is incredibly good at taking a news story in science and condensing it into a really short soundbite that people can understand and become enthused to then go away and read in more detail about it. He condenses long, complex things into the very key point to just get it across so that everyone can understand it really, really quickly. And I think that works amazingly for children, particularly. Children can just hear his soundbite and go, oh, that is so cool. And then they can go learn about it some more. And he also, you could tell from him that he was constantly looking for that next tag of the thing to say that would infuse people. So I talked to him for a long time backstage, and he was taking notes when I was talking to him, and he was writing things down, and he had a whiteboard and he was drawing things on it at that time. And then you could see he was building all these connections in his brain of like, oh, I can say that in this way, and I can change the wording there, and I can make that work, and I can explain that to someone. And it's a really impressive skill to be able to condense that science down into those small nuggets that get people infused. And I think I've tried to do that as well in all the stuff that I do. And I love talking to the public, and I love talking to children specifically about science, and also teaching undergraduates and high school students about astronomy as well. And I kind of see it as the same problem as doing scientific research, in the sense that what I have are a load of complicated things that I'm trying to piece together, and then I'm trying to find some coherent way to describe those things to my peers such that they understand the sort of model for a galaxy that I'm trying to convey. And in education and outreach, what I'm trying to do is take all of these complex astronomy ideas and distill them into a coherent sentence or infographic or presentation that somebody who knows nothing about science can understand, and that they can get something from it, and it can excite them about learning more. So to me, they're exactly the same problems. They're a way of bringing in all of these ideas and making a coherent narrative about them. And I get the same buzz when I've come up with a way that I think describes galaxy evolution to a 5-year-old as I do when I do some complex astrophysics and come up with a model to explain how a galaxy works. They completely scratch the same itch for me, because I feel it's a very, very similar problem, just in a completely different sphere.
No, I think, yeah, and I think you do a great job as well. I'm sort of obviously have no idea the complexity, but you've explained everything in a really approachable way, I find. And I think sometimes
you see a small child's face when they get it and it clicks and they understand, and it is like the best feeling in the world, because you're just like, that kid is going to go away from this interaction being more excited about science than they were before. And if I can do that, then that I hit the nail on the head, and that's perfect. And if I go out and I talk to hundreds of children, and one of them goes off to do something interesting in science, whether it's astronomy or anything else, or medicine or biology or engineering, if even in a tiny part that conversation helped them along that journey, I'm super proud of the fact that I got to be part of that. And that's why I really just love talking to children all the time and trying to enthuse them about having careers in science and STEM.
I think you're doing an amazing job with your own, science communication, and it sounds like you're doing amazing work on the, actually the scientific side of things, but also in the, going around and bringing the word to kids and trying to inspire the next generation, which is very
I definitely
commendable.
Do it for me. It makes me feel good. It's a purely selfish thing.
That's even better. It makes you want to do it even more, I reckon, then, if you really, really enjoy it. So no, that's, I've had a great time today, mate. You've taught me a lot, and it's a fascinating sort of area, and hopefully some of the listeners can take a few bits of nuggets of information away.
Yeah, no worries. If you find that any of it's not clear or it cut out or anything, just let me know. I'm happy to jump online and repeat some of the stuff I said, or say something different if you need any more. There's no worries.